Welcome back for part 2 of chapter 8, section 8 of the pre-algebra notes. We are still graphing linear systems, and we are also solving linear systems. So we are down to example 4 now. We are talking about ecologists studying the population of 2 types of fish in a lake. We're using the information from the table below, and we are going to write 2 linear equations. Those 2 linear equations will be our system of linear equations, and our goal is to figure out when the population of the fish will be the same. Let's look at fish type A. Fish type A has a current population of 340, and it's changing by 25 fish per year. But the change is negative, so we are losing 25 type A fish each year. Fish type B has a current population of 180, but it is increasing by 15 per year. So we are going to write linear equations to represent these situations. The current population, that's the starting point. What variable in a linear equation represents the starting point? Yes, it would be the y-intercept. So this starting point would be the b in our linear equation, and the rate of change. It's changing. Which variable, which part of the linear equation is the rate of change? Okay, yes, it is the slope. So m. Slope, the rate of change is our m. So let's look at fish type A. We're going to write a linear equation to represent fish A. If we're changing or we're decreasing by 25 fish per year, we are going to plug in negative 25 where the m would go, multiplied by x, and our current population is a positive 340. So that is the equation for fish A. Fish B. Fish B has a rate of change, a slope of 15. So that's going to go where the m would go. 15 times x, and a current population of 180 plus 180. Okay, the next step says, in order to find the solution of these 2 equations, we need to plug them into a graphing calculator. Unfortunately, I have not yet taught you how to use the graphing calculator, so we need to come up with a different way to solve this system. You can feel free to pause the video and see if you can come up with a way that you can solve this system without graphing. Okay, I am going to show you how to solve a system of linear equations without graphing. So you need to figure out at what point these 2 fish populations will be the same. So you need to find out when they will be equal. So one way that you can solve this is to set the 2 linear equations equal to each other. So we are going to take the expression that represents fish A, in purple, fish A, negative 25x plus 340, and we are going to set it equal to the expression that represents the population of fish B. When we solve this equation, it will tell us the value of x, which represents the number of years in which this will occur. After how many years will the fish population be the same? Solving this will give us our x value. So let's solve x and find out after how many years the fish population will be the same. I want to move 180 to the other side of the equation. So we are left with, bring down your equal sign, we're left with 160. We're left with negative 25x. Those cancel out, and that's equal to 15x. Now let's move negative 25x to the other side of the equation using inverse operations. Remember, 15x and 25x are the like terms, so they are the ones that can be added together. So we're left with 160 equals 40x. The last step, inverse operation, divide by 40 on both sides. So we know x equals 4. If x equals 4, and x is representing time in years, we know the fish will have the same population in 4 years. Now, the other part of the question was, what will the actual population be? Now, that's y. Y is representing the total number of fish after x years. And we know x is 4. So what is the total number of fish after 4 years? Well, now all you have to do is plug the value of x, 4, into both equations to make sure it works. They should be the same. So I'm just going to scooch over here, and I'm going to rewrite this same expression I have already. Negative 25x plus 340, that's fish A, equals 15x plus 180, that's fish B. Since we know that x equals 4, I want to put x into this equation. And when I solve, both sides of the equal sign should be the same. Then I will know I am correct. So I'm going to plug in a 4 here, and a 4 here. I'm going to bring down the rest of the equation. Whoops. Okay, now all you have to do is solve both sides of the equal sign. Let's do the multiplication first. Negative 25 times 4. That would be negative 100 plus 340 equals 15 times 4 plus 180. So we'll have 60 plus 180. Now let's go back and do the addition on both sides. Negative 100 plus 340. That is subtraction. 340 is the greater absolute value, so the answer is positive 240 equals 60 plus 180, which equals 240. So not only have we proven that the system is correct and x does equal 4, but we also found our value for y. Y equals 240. So our coordinate that represents the population of the fish when population A and population B will be the same is 240. After 4 years, the population of A and B will be the same, and it will be 240. 40. After 4 years, the population will be 240. So there we go. Now you have a new way to solve linear systems without graphing. I would also like to give you a couple of practice problems just to make sure you're ready to go with the rest of the activities. First practice problem, you're going to see some problems on your practice page that ask you to tell whether a certain coordinate is a solution of a linear system. Whether there's 1, 2, or 5 equations in your linear system, you have to plug that coordinate into all of them, and that coordinate needs to be true for all of them. So let's try this one. Your coordinate is going to be 0, 9, and your system is y equals negative 5x plus 9, and equation 2 is 6x minus y equals 11. So this is just asking you to tell whether the coordinate 0, 9 is true. Is it true for this system? So I don't know why I put 0, 9. Is it true? So all you are going to use for this is substitution. You're going to substitute. Substitute. That's spelled correctly. You don't have to put anything in slope-intercept form. You don't even have to graph. You are just going to plug in the values. So looking at the first one with the values plugged in, you are going to get 9 equals negative 5 times 0 is 0. 0 plus 9 is 9. So 9 equals 9. The first equation is correct. 0, 9 works for the first equation. Let's look at the second equation. 6 times 0 minus 9. 6 times 0 is 0. Minus 9 is negative 9. So negative 9 equals 11. Negative 9 does not equal 11. So this coordinate is not true. So this is no. Not a solution. No way. Whoops. Now for this example, you might be asked to graph these these three equations in the system. Now there are 3 linear equations in your system. Well, if you look right here, they were not given to you in slope-intercept form. So the first step would be to put them in slope-intercept form. So the equations you would actually be graphing are now over here. So let's graph these 3 equations. Here are the equations graphed. What did we make? What do you see? I see a triangle. Can you identify the vertices of this triangle? The vertices of the triangle would be formed by the intersection of those lines. So let's see what these vertices are. Here's one. What's the coordinate of this vertice? Let's see. 1, negative 1, 2, 3. So 1, negative 3. There's one vertice. How about this one up here? 1, 2, 3, 1. 3, 1 would be that vertice over there. And the last one right here is negative 1, 1, 2, 3, 4, 5. Negative 1, 5. So there you have it. You can also use linear systems in geometry.